Okay, we're going to go through one more example of a hypothesis test. And in this hypothesis test, first of all, I see a typo already. That's a 4 there. Okay. In this hypothesis test, I'm looking at one proportion, and I'm testing that against a specified value. We will consider 3 methods: the confidence interval, the cutoff values, and the p-value for doing this hypothesis test. So let me read the problem first. Since becoming an expansion team in 1961, which at that point they were the Washington Senators, the Texas Rangers, which is what they now are called, they've won 3,747 of their 7,959 games. They have won 331 of their 648 games under the current manager, Ron Washington. If each game is thought of as an independent Bernoulli trial, perform a hypothesis test on the claim that the probability of winning under manager Washington is larger than 3,747 divided by 7,959. Use alpha equals 0.05. Okay, I see another typo. I'm going to fix that real quick here. Okay, so this data I pulled, it would have been over spring break. So this is probably about a month old or so. And we have the data since the baseball team became a baseball team, and then we have the data since they've been under their current manager. And the question is, have they been better under their current manager? We're going to perform a test that says that they are better. Okay, or at least that's the claim. Our claim is going to be that they are better under manager Ron Washington. And I am not a great big baseball fan, but I thought this might be an interesting example, so I looked it up. Okay, so what are we really trying to get at here? The underlying random variable is x, and that random variable we're going to assume is Bernoulli. Maybe it's 1 if they win a game, 0 if they're not. And p is the probability that x equals 1. In other words, p is the probability that the Rangers win a randomly chosen game. Okay, we have a nice point estimate for p. Okay, if indeed all the managers are the same, in particular if Ron Washington is no different than the other managers, then p would be 3747 over 7959. That would be our good estimate for p. However, notice that under Ron Washington, Rangers have been better than 50%, whereas this is less than 50%. So it makes you think that maybe their probability of winning under Washington has actually changed, and it's no longer equal to this 3747 over 7959. Okay. Now, you might say, wait a second. I said one proportion. Why is this one proportion and not 2 proportions? Because there are 2 proportions running around. I got 331 over 648 and this other proportion. The reason we consider this a hypothesis test of one proportion is that we're only going to consider the variation in this sample, in this smaller data set. We're going to consider all of the games as the population that's under study. So it's a proportion, but it isn't a sample proportion. We're not taking a sample, and in particular, we're not considering variability within this 3747 over 7959. So when we get x bar, all right, of our 648 games, under the null hypothesis, that's going to be normal. Well, I guess whether it's a null hypothesis or not, it's going to be normal with mean p and standard deviation. Let's see. The standard deviation of a Bernoulli random variable was square root of p times 1 minus p. And then if we're doing an average over 648 games, that's the square root of 648. Okay. So if the null hypothesis is true, then we have the x bar is approximately normal with mean 3747 over 7959, right? That's the case if Ron Washington's the same as every other manager. And then what's the standard deviation? Well, it's this nasty thing. So we have, let's see, the square root of 3747 47 over 79.59, and then we multiply by 1 minus that. So let's see, that would be 42.12 over 79.59. I bet that by now Stephen has looked up and seen, made sure that these numbers are right. So I checked this over spring break. I'm guessing it included data up to spring break. It might have just been up to last year, Stephen. So please do let me know if you find an error, but I don't think I'm going to remake the video if that's the only error. Anyway, we want to divide by the square root of 648 here. All right, so if we're going to do a confidence interval, whoops. Well, that's our first method of performing a hypothesis test. Alpha is 0.05, so we would use a 95% confidence interval. Again, if alpha were 0.1, we'd have a 90% confidence interval. But we do a 95% confidence interval. For p, the parameter of the Bernoulli random variable. Well, we've seen, you've done several examples, you've seen that the endpoints of that confidence interval are 1.96 standard deviations away from the mean. That's the magic number. So our confidence interval is going to look like the sample mean that we observed, which, let's see, that was 331 out of 648. So it's going to be 331 over 648 minus 1.96 times all that, the square root of 3747 over 79.59 times 4212 over 79.59 over the square root of 648. And then the other endpoint of the confidence interval, I'm going to get fancy here and use some copy and paste, is just going to be that same expression with a plus sign. Okay, so let's go ahead and enter this into the calculator. If you are pressed for time, I encourage you to fast forward through this part, because it will take me a little while to get this in the calculator. Actually, I think I'm going to compute that standard deviation by itself before I go and add it and subtract it from the actual sample mean that we saw. 79.59. Okay, I'm going to take that expression and I'm going to, let's see, square root that. I think, yep, there we go. And then I divide by the square root of 648. Okay, so I'm going to store that in memory. I do memory plus for that. And now I'm going to take 331 divided by 648 minus memory recall. That gives me 0.472. So I got 0.472. And then I'll do 331 divided by 648 plus memory recall. Why do you not like that? Okay, there we go. Equals, oh, I see it. Didn't want to close my parentheses. 0.549, I believe it was. Yes, 0.549. Okay, so there is our 95% confidence interval for P. Now, this value that we're testing against, 3747 over 79.59, that's about what? Well, let's see, 3747 divided by 79.59, that's about 0.471. So it just misses it. It just misses it. And this proportion is actually not in that confidence interval. In other words, This test supports the idea that the rangers have a higher probability of winning under the current manager than they have overall. Okay, so it just made it. It was really close, but the test ends up supporting the alternative hypothesis that their probability of winning under the current manager, was it Ron Washington? Under Ron Washington, is actually higher than what it is, or is actually different than what it is with other managers, or the other managers that the Rangers have had. Okay, so that was a confidence interval approach. Now let's take a look at cutoff values. Again, the cutoff values feels pretty similar. The difference is, instead of wait until the end to introduce this value that we compare to, we start with what we're comparing to. And instead of starting with the sample mean, we're going to wait till the end to introduce the sample mean and examine it. So our cutoff values are going to be 0.471 plus or minus 1.96 times times that standard deviation. And I'm just gonna, for brevity's sake, actually I guess, you know what, I can do this again. I can copy and paste this feller. So let's see, we'll do Control C, Control V. Probably should have. Okay, 1.6 times that. Alright, saved us all some time here. And furthermore, I already have this expression stored as memory in my calculator, so this won't be too long to compute. We have 0.471 plus that value in the calculator. So the first cutoff value is 0.509. 0.509, and the other cutoff value is 0.471 minus that which was stored in the calculator, which is 0.433. Okay, now our actual value was 331 over 648. And let's see, we have 331 divided by 648. That gives us about 0.511. Since this guy does not fall between those two values, okay, again, the alternative hypothesis is supported. And I'm saying it different every time on purpose, because there are different ways to say this, but it's the same idea. So the alternative hypothesis is supported. In other words, the difference is statistically significant. Okay, and finally we'll use p-values. Now p-values are a little different. We say that if we assume the null hypothesis, okay, what is the probability that we get a result more extreme than what we actually saw? What's the probability that we get a sample mean more extreme than what we actually saw? So to get that, we compute the z-score under the null hypothesis. And I have it written down on my desk here, so I'm not going to keep scrolling up. Our measured sample mean, our measured proportion, that's where it comes from, we're doing one proportion, is 331 over 648. And what we're comparing it to is 3747 over 7959. Okay, and then we divide by the standard deviation, which is this nasty thing. This nasty thing, and actually I think I'm going to make that transparent. Okay, so let's pull up our calculator here, and I get, let's see, 331 divided by 648 minus 3747 divided by 7959. Now I'm going to have to get a little bit tricky here. This value in memory was that standard deviation times 1.96. So I'm going to need to take that value and divide by 1.96 to get back the standard deviation, and I get about 2.04. I get about 2.04. Okay, so if I look on a normal, if I look on a normal distribution table, okay, there's my sample mean. In other words, the proportion that I saw, it's going to give me this area for 2.04. And if I scroll down here, then I have 2.0, then here's 0.00, 0.01, 0.02, 0.03, 0.04. So it's 0.9793. 0.9793. The p-value is the probability that we're more extreme than that under the null hypothesis. So if indeed the proportion's truly equal to this nasty 3747 over 7959, that's the probability that we get a sample mean or a sample proportion that's further away from that than what we actually saw. That's our p-value. That's what the p-value means. So each one of these tails is 1 minus this, so it's 0.0207. So if I double that, I get a p-value of about 0.0414. And these are approximations because, first of all, this z-score is an approximation. Second of all, that which is on the table is an approximation. And since this time we have p-values less than alpha, the alternative hypothesis is supported. In other words, the null hypothesis is rejected. We reject the idea that there's no difference between these managers, and instead we support the idea that the team tends to do better under Ron Washington. All the while being well aware that it could just be due to chance. It could be that the team was especially lucky. And notice there's lots of other variables here. What players have they had? How have players been in other teams, etc. There's a lot of other variables, and those other kind of variables are always around. And in statistics, it's common to do stuff like this, where we try to isolate the one variable. And we know that this is really an idealistic world, and we're leaving some things out, but gosh darn it, that's just what we have to do to be able to get anywhere. We've got to focus in on what very well may be the most important aspect, and then do a test and see if that looks like it is an important aspect. And we can consider our data in the aggregate and not just look at one test isolated by itself. Okay, so again, we did 3 tests. This time, instead of doing one mean, we did one proportion. And again, that was one proportion because this proportion was the only one we were considering as variable. The other proportion we only used to compare it against. In the next section, we will talk about an example of where you would consider variability in both proportions. It's not a whole lot different, but it does get a little bit more complex. We looked at the confidence interval, and the confidence interval did not contain the value we were testing against. We looked at cutoff values, and the actual proportion we saw was outside the bounds of those cutoff values. And then we looked at p-values, and our p-value was less than 0.05. All of those signify that we should reject the null hypothesis and support the alternative hypothesis that the team tends to do better under manager Ron Washington. Okay, so in the next and last section of this course, we're going to go through and look at a few modifications of this hypothesis testing. First, we're going to look at using t-scores rather than z-scores. In our examples, we've had a way to come up with sigma. What's the standard deviation for the population under the null hypothesis? Sometimes, however, you have to estimate the standard deviation based on the sample data. That adds a new level of variability variability to things, and you want to use a t statistic rather than a z statistic if you're estimating that standard deviation. Second off, we'll talk a little bit about one-tailed tests versus two-tailed tests, how they're different. And third off, we'll talk about using testing two means against each other, or two proportions against each other, instead of just one mean or one proportion against a specified value. Okay, so you're almost there. I encourage you to keep chugging along, and in a few weeks, you'll be done. And I hope that after you take a break for a couple of weeks, that you'll be back for the advanced calculus course that I'll be teaching during the summer one term. But first, let's get through this probability and statistics stuff, and we just got one more section to go.